Hi everyone, my name is Barnabé Monnot. I am a researcher at the Robust Incentives Group, which is a research team at the Ethereum Foundation. Today I will tell you a bit about protocol cryptoeconomics with the rig. I'm very disappointed that I have to do this remotely. I would much rather be here in Paris, which is also my hometown with you. But I'm very happy that you could make it and that you can see my presentation today. Let me just introduce very briefly what the rig is. So it's a research team hosted by the Ethereum Foundation that really focuses on everything that has a strategic flavor. And by strategic, we mean in the sense that we look at situations where stakeholders have to make decisions to optimize their payoffs, maybe to maximize their rewards, for instance. But these are also situations where your payoff is a function or is affected by the decisions of other stakeholders. So it's a very general model of strategic incentives and, let's say, decision-making, which is well suited to study things such as protocol security, cryptoeconomics. So I'm picturing here a few applications. You might know all of this under the name of game theory and mechanism design, but we've decided that cryptoeconomics is just much sexier. So this is a fourth choice, for instance. It's a model that's in fact well suited to study many other things like growth of cities or even transportation, which was actually my focus before getting into the Ethereum rabbit hole. Today, I want to give a brief overview of some of our latest results and discuss a bit our methodology around two specific applications. So we've done a lot of work on EIP-1559, which is a very important change to the transaction fee market. We've also looked a bit at the proof-of-stake protocol, so try to model the protocol in these stakeholders' game theoretic terms. And at the end of my presentation, I will show you a new model that was released last week, which is dedicated to provide economic modeling for the community. So let me start with EIP-1559. I should probably start by saying that Tim Bako, who is the amazing project manager of a lot of things in Ethereum, is actually going to be speaking about the road to mainnet for EIP-1559. It will be in this room in 1 hour. I will only give a very brief introduction, but if you want to learn more about the EIP, you should definitely go and attend his talk. But let me just briefly give you the gist of what is happening. So EIP-1559 is a reform of the transaction fee market, which adds dynamic congestion pricing. So the protocol adds this new, what we call base fee, a minimum fee, which is a constraint that says, okay, if you want to be included in a block, you have to pay at least the base fee. And the base fee is dynamic, so it varies block to block. And it varies so that it tries to equalize, to match demand for the chain, for execution on the chain, and supply of gas in the chain. So when more users want to transact, it's a sign that the minimum fee needs to be increased. We need to price out more people. And when less users want to transact, we can decrease it. We do that by doubling the size of the block. So we now have 15 million gas per block. After EIP-1559, the limit will be 30 million, but we still target 100% fullness, so 15 million gas. And we use that as a kind of objective oracle that tells us whether blocks are getting too full, if they are reaching max capacity, or if they are not full enough. And we use that to vary the base fee. So users declare on top of the base fee what they wish to add to that minimum fee, and they also declare their maximum fee. And they end up paying the current base fee plus this priority fee that they have declared. Right, this is a very 2-minute discussion of this. Please go check out Tim's talk later. So what have we done for EIP-1559? We've done what we call agent-based models. I mean, we don't call them that, they are called that in the literature. It's a very well studied form of modelization. The general idea is to code simple behaviors, simulate, so code simple agent behaviors, and just let the simulation play out, and kind of at the end of the simulation, try to interpret the outcomes that we observe without necessarily specifying where we want the simulation to end up. So we just code the basic rules, the transition, and we observe how things unfold over time. Here is one of the most famous agent-based model, which is called the Schelling segregation model. It's a very simple interacting rules. We start from a random state at the beginning, and at the end we observe maybe something that like an emergent phenomenon, and we try to understand why it happens. So to simulate the fee market, it's a bit more complex than this Schelling model. We have first agents. We have two types of them. We have users who want to transact, so they have a certain value for their transaction, and they have different bidding strategies. And you also have block producers who are responsible for the management of their transaction pool and for their inclusion strategies. And so we have these two types of agents. They coexist in this environment. So the environment can be any fee mechanism. So we've modeled current fee mechanism. We've also modeled EIP-1559. We've modeled an alternative proposal called the escalator. Anything can be modeled. And we just let the simulation play out, and we try to understand what's going on. I've left the link here. This is where you can find some of our results. So simulations are nice. They really give us a view into this emergent phenomenon that sometimes we may not expect, in fact, to arise, or we can kind of anticipate what the fee market will look like once it's deployed. We really need to de-risk as much as possible these big upgrades to the protocol. So the more information we get ahead of time, the better it is. And in fact, these simulations also sometimes give us clues as to things that we can formalize. And this is what we've done in this paper with my co-authors, Leonardo et al. You can find it on arXiv. We've managed to prove some results around the stability and the instability of EIP-1559 in general cases, as well as more pathological cases. One of them is plotted here. So this kind of workflow, starting from simulations, trying to get ideas of what could happen, being able to formalize what we can, this is very helpful. And it's definitely laying the groundwork for the work that we might be called to do in the future, which is how do we tune EIP-1559? How do we interpret things if they go wrong after it is deployed? So there are many things that are possible, but we definitely at this point just need to get data first. So we're looking forward to the August 4th launch to validate first our simulations and also some of our formal results. One big thing that we emphasize in the rig is the idea of open source and open science. All of our results, all of our simulations are basically based on notebooks. So these notebooks are available in our repository. We really focus on this aspect of reproducibility and try to make the notebooks as reader-friendly as possible. So you have access either to the raw notebook or to HTML version of it. And what's been really nice is that we've seen now the community has sometimes used these notebooks to make their own simulations and to try and extend them in ways that were maybe unexpected from me and the team. So this is EIP-1559. I will now talk about proof of stake, which we are not allowed to call ETH2 anymore. We have, again, tried to do as much as possible simulations to understand the system. The starting point was a little bit different because the specs for the Ethereum proof of stake are very well written, and we took that as kind of ground truth for our simulation. But to zoom out a little bit, the idea is to adopt the view of blockchains as these controlled dynamical systems. So they are systems because they have like many moving parts and they have some kind of state, which is the current chain of blocks, so like the data. They are dynamical because you have updates. So a block is added, this adds more information, there are transition rules. And it's controlled because you have users and validators in proof of stake who participate in consensus and who kind of steer the system towards certain states. And so as I was saying before, what we've done is adopt this view, try to abstract from these Python executable specs, which is really the ground truth for the Ethereum proof of stake protocol, and abstract from this as much as possible to arrive at the strategic representation of validator behaviors. So we couldn't abstract too much. We still had to do a little more, such as simulating the propagation over the peer-to-peer layer. But we arrived at this model where we're able to specify very simple, let's say, validator behaviors and make it look like this agent-based model. So validators can be either honest or rational or offline, these types of behavior. We try to simulate and we try to understand, well, if validators are doing what we want them to do we actually get the outcomes that we expect to get? And interestingly, sometimes we don't. And I think two ways that the Beacon Runner has been helpful are these. The first one is payoff testing. So the proof of stake consensus is actually fairly complex rewards that it pays out. There are many different sub-mechanisms which kind of interplay with one another. And recently we were able to figure out that some of the rewards that we expected to be paying out to validators, it was actually not quite by a few percentage points. So this was helpful to just simulate and collect these results. And the second way that it's interesting to do this is to really do this strategic testing. So we have this idea that validators should do their job honestly, and we have some kind of specification for that honest job doing. But sometimes a validator could be doing something else, maybe being a bit late or sending wrong votes and somehow making a higher profit. So in the proof of work, for instance, you can think of selfish mining as such a deviation. And with the Beacon Runner, we really hope to isolate these kinds of strategic questions and to have a clearer view of whether the protocol as defined is indeed rational for the validators who follow them. One notebook about the payoff testing is available here. It's about Altair. Another notebook which was kind of looking at this idea of strategic deviations is also available at this address. Another thing that we are quite focused on, besides simulation, is also data analysis. So we try to understand not just the protocol from this virtual, let's say, point of view, but even see it run, try to collect data, try to monitor some critical metrics, study also some dynamics as they play out, and potentially, if we are called upon to, diagnose issues when they arise. So we've done, for instance, a deep dive into the aggregation mechanism of the votes in proof of stake for the first 1,000 epochs, which revealed some perhaps inefficiencies or ways that the protocol could be more optimized. And I also encourage you to check out these Beacon Digest notebooks, which are produced by Shyam Sridhar, who's an intern with us this summer. He's been publishing every 2 weeks, kind of like a summary of what has been playing out in proof of stake, and using research papers to orient his analysis. All right, so at this point, I will introduce this new model for Ethereum Economics. We believe it's important to understand the economics of Ethereum, of course, but all the more so because things are changing very rapidly. These two previous topics that I discussed, EIP-1559, proof of stake, they drastically change the way the economic ETH as an economic asset behaves. So EIP-1559 adds this sink to the ETH asset. The ETH that is collected from the base fee is burned. So it's a way to remove it from the supply. And proof of stake on its own will also considerably reduce first the cost of securing Ethereum, but as a consequence, also the issuance almost tenfold compared with proof of work. And in fact, the issuance will be much more also variable compared to proof of work, and it's 2 Ether per block reward. For proof of stake, we have instead this sliding scale where validators earn more or less rewards on their stake, depending on the number of validators in the system. So there's, again, like more moving parts, and moving parts that are really inherent to the Ethereum protocol, and so it's very important to understand them. Given this complexity, there's definitely been The challenge was taken upon by the community to try and do that. It's critical to model these long-term effects and understand possibly economic interaction, not only at the protocol level, but between the protocol and other applications. For instance, Pintail has been looking at the validator rewards, and then Flashbots has used this model to model the impact of MEV for validators in ETH2. I believe Alex from Flashbots is also going to talk about this either soon or later today. There's been a few economic calculators based on spreadsheets. The ultrasound money people have recently released their own front end to model the deflation and the burn. They're very focused on this. And finally, Rocket Pool, which is a staking provider for non-custodial validators, has been releasing also an analysis on the post-merge APY. So there's definitely like a lot of moving parts. A lot of people are looking at it. And what the CAD Labs team, which is a team that received a grant from the Ethereum Foundation, has done, they've created this very extensible, very well-designed Python-based model that contains the basic protocol dynamics, such as proof-of-stake validator rewards and costs, the EIP-1559 fee market, validator adoption patterns, as well as different price models. All of this is included in the model kind of out of the box, so that anyone can take that model and either play with the parameters themselves, run their own analysis and scenario, or extend it. So it's been designed for modularity and extensibility. So you can extend it to also understand maybe the impact of different parts of applications on the protocol or on these economics. It's fully documented, and it comes with a few notebooks that kind of show you how to use the model and also provide some analysis. It's built on this new library, which is CAD, and in particular the RADCAD implementation of CAD. So this is very helpful to provide this extensibility. And another good news is that it comes soon with an online masterclass, probably by the end of the summer, where you will be able to first learn a little bit about the Ethereum proof-of-stake protocol, but also learn how to use the model and run your own analysis. So I encourage you to try it out. You can find the repo online on GitHub at this address. You can also contact the CAD Labs team for a model overview at the CADLabs.org Twitter handle. Or you can also find me on Twitter. We've been collaborating with them to build this model, and I'm happy to hear what you intend to build with it. That's it for me. Enjoy Paris. Very sorry that I cannot be here, and thanks for tuning in. You can find most of the things I've been discussing today at our homepage, ethereum.github.io/rig. Thank you. So what do you mean by censorship resistance? Like the action of miners who would be blocking, for instance, users from having their... Right, so... Sorry? Right, so for instance, there's been some modeling around can miners collude to do something bad to the fee market? You can model that, for instance, with the EIP-1559 simulator. You could find, for instance, bounds. Let's say you could simulate the action of some group of miners colluding and another group playing fair. And you could probably find some bounds on the amount of censorship resistance that the system has given some level of collusion in the system. For proof of stake, the guarantees are slightly different. So you have this protocol that provides, let's say, accountable finality. So you know that if a group of validators suddenly colludes to try and stop the protocol from finalizing, so from providing safety guarantees for proof of stake, you know that there are some kind of emergency scenarios where you could fork out these validators who do that, or you could recover from attempts at censorship differently. So you can of course model both of these scenarios either with the beacon runner or with the EIP-1559 scenario. Possibly what you would get from simulations that you couldn't get from, let's say, a more formal analysis is these bounds that might depend on kind of random events. When are you allocated slots to propose a block? When are you, what is your inclusion strategy? These sorts of things, yeah. I hope that answers your question. Okay then. Thank you.